Let's remind ourselves about the things that we should have gotten in our notes from the Endo-Exo lab. We have two situations, and I suggest that you get very familiar with this diagram. In this case, the energy of the reactants is greater than the energy of the products. That means that our delta here will be negative or less than 0. Delta H is negative. Energy has gone downhill. That energy that comes out of the chemicals in our system heats up the surroundings. So our change in temperature is positive. And this then is exothermic. So I would very much suggest draw this diagram. Make sure that you've labeled it as exothermic so you know which way the reactants and the products go. And make sure that you note that when delta H is negative, delta T is positive. This is what we saw in our magnesium and hydrochloric acid. It was exothermic. Our other situation then is what we saw with our citric acid and sodium hydrogen carbonate. The energy of the reactants is less than the energy of the products. So our delta is positive. This means that energy has had to go uphill. We've had to put energy in to make these products. Energy has entered the system, and it had to come from the surroundings. So that means that the change in temperature is negative when delta H is positive. And this is, of course, endothermic. Energy entering the system is endothermic. So again, I would make sure I have this diagram so I remember the way the reactants and the products go for an endothermic reaction. And I would also make sure to note that when delta H is positive, delta T is negative. So here's a little problem. So from this reaction profile, let's calculate the change in enthalpy, delta H, for the reaction. Of course, delta is final minus initial, or in our case, where do we finally end up? Products minus where we started, reactants. So if we look at this, we can actually estimate these numbers to be about 300 for the products and about 100 for the reactants. So our delta H is 300 minus 100, or about positive 200 kilojoules. And this means that that is an endothermic reaction profile. The products are higher energy than reactants. Since our delta H is positive, we would see a negative delta T. So another way we can write this sometimes is we can sometimes see it in the context of a chemical reaction. For example, I have this one here, which is burning propane. Hopefully, thinking that burning something is exothermic is not too surprising to any of you who have a gas grill, because this is the gas that is burned when you grill a hamburger or a hot dog. So burning something makes the things around it warmer. It's exothermic. We can see that from the negative delta H. In this chemical reaction, they wrote the equation, they give us the delta H value out next to it. We see that the delta H value here is a positive number. And that tells us that this is endothermic because delta H is positive. The other way we can see this is to write it actually into the reaction itself. And then I have to think, is this energy, this kilojoules, are they leaving the reaction? Like a product leaves the reaction? Or is it going into the reaction like a reactant? In this case, I see that the kilojoules are on the product side, so they must be exiting like the product exits the reaction. So if energy is exiting, you can hear it in the word, that is exothermic. When delta H is a product, that is an exothermic equation. Here we have the delta H on the reactant side. They didn't give us a particular number. They just told us that the enthalpy change is on the reactant side. So that means we had to put energy into this reaction to make it go. And that is endothermic. We had to put heat into the reaction just like we have to put reactants into the reaction. Another thing to notice is that enthalpy change is extensive. Remember, an extensive property changes with the amount of the substance. And we saw this in our endo-exo lab. We used the 3 different pieces of magnesium, and we saw that the amount of heat generated, which is equivalent to our enthalpy change, it's the opposite in sign of our enthalpy change, we saw that we got more heat generated from the larger strips and less heat generated from the smaller strips. The more we had, the more heat we found. That means that we can say this in terms of mass, or we can say this in terms of moles. The more moles of a reactant are involved, the greater the enthalpy coming out of a reaction. So delta H is extensive. That means that we're going to have to multiply the enthalpy change for 1 mole by the number of moles. So if 1 mole has a delta H of minus 100, 2 moles is minus 200. So oftentimes when we see this, we will see this with a particular unit, kilojoules per mole reaction. So we need to think about, what does this unit mean? Obviously, kilojoules are a unit of energy. And the mole of reaction is actually pretty simple. It has to do with the balanced chemical equation. 1 mole of reaction is 1 time through the balanced chemical equation, exactly the way it's written on the page. So in this case, 1 mole of methane is equivalent to 1 mole of reaction. But in 1 mole of reaction, I use 2 moles of oxygen gas. This is really a case where using our units is going to be very important. So when I look at this problem, I see that 5.8 grams of methane is burned. But I notice that my unit here is 890 kilojoules released per mole. So the first thing I have to do is think, well, if this unit is per mole, then I need to get these grams into moles. I'm going to take this 5.8 grams, and of course we'll divide it by the molar mass of methane, and we'll find that we reacted 0.36 moles. But this is moles of methane. And if you write that down and you show your units, it will help you to remember to look at the stoichiometry. Because just like in the stoichiometry unit, where we knew we couldn't cancel a mole of oxygen with a mole of methane, we had to deal with the mole ratio. We can't cancel the mole of methane with a mole of reaction. So if we think about what happens here with this unit, we see if I write down moles of methane, I can't go directly to this delta H value because that's per mole reaction. So I have to use moles of methane on the top, moles of methane on the bottom, and I look at the balanced chemical equation. 1 time through the equation uses 1 mole of CH4. Now I have moles of reaction on the top to cancel the moles of reaction on the bottom of my delta H. And since this is energy being released, and this is burning something, so this is exothermic, we have a negative here showing energy exiting. And we'll round that to our 2 significant digits for 2 significant digits in our data here, on 2 significant digits in our original data as well. And we get 320 kilojoules of energy released, minus 320 kilojoules. So the mole-of reaction is a really important step. In this particular case, since the ratio is 1 to 1, you feel like you can skip it, but it's a bad habit to get into because when the ratio is not 1 to 1, it's very important, and you want to be in the habit of including that so you don't forget it when the time comes that you need that to make sure your answer is correct.